So in addition to being an industrial designer with the Damani Group, I'm also an avid builder of furniture and collector of mid-century design. And this presentation is kind of a culmination of some of my passions, and it's a bit of a pet project for me. I love mid-century furniture, and especially the work of Ray and Charles Eames. And so I'm going to be showing you some tips and tricks I use in SolidWorks through 3 different Eames chair designs. The Eames LCW Lounge Chair, the Eames Fiberglass Shell Chair, and finally the Eames Lounge Chair. Charles Eames once said, "The details are not the details, they make the design." And I think this quote is quite pertinent for when we're working in SolidWorks. As SolidWorks is a really powerful tool for delivering design to us. However, sometimes we get caught up in the features that SolidWorks deliver us. Extrudes, revolves, fillets. And we don't necessarily focus on the details and the exact geometry that a part or design needs to be. So the Eames LCW chair is a 5-piece molded plywood chair. And here's the same chair recreated in SolidWorks. And we're going to be using this exact reference image and reverse engineering, not an exact copy, but close enough based on the available information we have from this photograph. A little background on the LCW chair. During the Second World War, the husband and wife team of Charles and Ray Eames, some people think they're brothers. No, they were actually husband and wife. They developed processes to mold plywood into compound shapes. This was initially used to produce medical splints used in World War II. They also produced a variety of aircraft parts out of their molded plywood. And their early lessons in the molded plywood led them to design multiple furniture prototypes, and this culminated in the LCW chair of 1946. As I said before, it's built of 5 pieces of molded plywood. The seat back and the seat pan feature some compound curvature, whereas the legs and the spine of the chair are relatively straight sections. The gentle curves of the chair were hand sculpted in an era before CAD. More than extrudes, revolves, and fillets we required to model this chair. We're going to have to use some of the surface features available to us in SolidWorks. So when reverse modeling, it's helpful to have the object to model available. If not, dimensions will have to be estimated from available dimensions. I was able to grab this dimension of the chair from a Herman Miller brochure. Herman Miller is the authorized manufacturer of the chair. And when grabbing information online, be cognizant of fakes. Many mid-century furniture designs, because they've been around for so long and they are so popular, they've been copied by certain less than scrupulous manufacturers, and the dimensions can vary from the actual product. They may not get the details quite right. And if the original item is unavailable, try to find similar references. I happen to have a DCW chair, which is the dining height version of the lounge chair, in my collection. As well, I have an LCM chair, which is identical to the LCW chair. However, it has metal legs. In case you were wondering what some of these acronyms mean, well, Ray and Charles were quite poignant in their naming of chairs. The LCW is a low chair wood, a DCW is a dining chair wood, and you guessed it, a LCM is a low chair metal. So, setting up the modeling in SolidWorks. We're going to be using that reference photograph I found online as a basis for modeling the chair. I'm going to be able to get some additional details on the construction of the chair based on the dining chair I have in my collection, as well as being able to get some form of the seat back and the seat pan from the LCM I have. So in order to get the reference photograph into SolidWorks, we're going to start a sketch on the right plane, and we'll use tools, sketch picture to get that in there. I'm not going to demo that live just because 50% of the time I happen to get a crash in SolidWorks 2014. By the way, I don't have access to the newest version of SolidWorks. Not because I don't have it on my computer, but being a consultant, I have to use the version of SolidWorks that my customers are in. In this case, most of the work I'm doing is in 2014 and 2015. So I don't want to talk about 2016 just because I haven't had a chance to use it, and I don't know if what I'm telling you is valid or not. So everything you'll be seeing in this presentation today is valid in 2014. As well, we're going to be going pretty quick. You may miss some things on the PowerPoint slides. However, the Damani Group, we will be hosting this presentation along with some of the example files on our website. So I invite you after the presentation, come up. I'll have a stack of business cards. Grab a business card, grab the website address, damanigroup.com. All I ask is that if you take a business card, you leave one of your own. Thank you. So into SolidWorks here. So here we have the whole assembly of the chair. or got it faster. McMaster Carr was a great resource of that, but let's take a look at the individual components that went into the chair, starting with some of the setup work to reverse model this chair. So I have two sketch pictures. The first sketch picture on the right plane shows a rough profile, and I had to take some liberties when using this photograph because the camera introduces perspective and foreshortening. If we zoom in, we see that the back leg is actually not in line with the front leg. This is not that the back leg is shorter than the front leg, it's just the camera causing foreshortening. Likewise, I can see both edges of the seat pan. It's not a true right section view. So I started by creating sketches on the edges that were most clearly visible to me, in this case, the bottom edge of the seat pan and the back edge of the seat back. I started a sketch and started throwing dimensions in. The dimensions are not necessarily the ones that will go on the drawing and be used to manufacture this part. It's more of a way for me to lock down and constrain geometry and be able to make small edits to the dimension as I look at the shape and maybe see that it needs to be tweaked to match the physical object that I have in front of me. I used a style spline. For those of you who attended my session on Monday, Surfaces and Splines, you'll note that I'm a huge proponent of the style spline tool. This is new in 2014, and I find that it creates really, really nice geometry. This purple section you see here is the curvature comb. This is showing the change in the radius of this curve. I've added the equal curvature relation to this edge here. What this means is that the radius is slowly decreasing to 0 because a straight line has no radius. So with the setup work done on the right plane, I've also changed my sketch colors to black to make it a little easier for you guys to see. I also inserted a separate photograph I found online of the front of the chair. Oh, wrong plane. And now I'm upside down. There we go. So this was useful for me to guess the angle of the legs, 8 degrees, and it looks like 19 inches between the front legs. I'm also kind of having to guess on the distance of the back legs due to that aforementioned camera foreshortening. Also, the seat back profile probably won't be correct. I won't be able to use that to later trim out the seat back because the seat is at an angle compared to the angle of this photograph. The next thing I did was I like leaving these layout sketches in the top of the tree, so I'll convert entities into a new sketch using the convert entities. And here I dimensioned to virtual sharps in the original sketch. This was a little easier for me to lay out. And then I just added sketch fillets to match the radii that I saw in the photograph. I then offset as a reference. However, I'm not going to create solid geometry right off the bat. When working with molded plywood, there's a technique I've been using that relies entirely on surface geometry. So the first feature I create is a surface extrude on the right plane to create the spine. I'm creating the inside of this, and later in a child part, I'm going to use a master model workflow. The master model workflow to me is a little better when I have to line up all these parts together. So I'm going to create all the surfaces in this part and then push the surfaces into child parts, and then detail and thicken the surfaces in those child parts. So a simple surface extrude on the right plane, and the back of the spine has a bit of a taper here and a radius on the top. So I can't cut a surface feature, but I can use a trim, and the trim gives me the taper and the radius on the seat back. But I'm going to take a look at the top of the spine, and I don't have perspective on. What's happening is the trim can't be controlled. It goes through the entire part. I can't specify go in this direction or specify a distance. It's essentially always a through-all cut. So the workaround here is instead of using a trim, I can use the split line tool to specifically target the faces I would like to have the cut on, and then use the delete face tool to remove those faces from the model. So here we see the setup in SolidWorks. I'm getting what I can from the photograph and being aware of the camera foreshortening that's happening and adding my sketches around it. And the master model workflow. So here we see the completed 5 surfaces of the chair, and then I'm going to use that part propagate it into the child parts, and then solidify and detail each of the components in separate parts. We're starting with virtual sharps in our layout sketches just because I find that easier to work with. Add the fillets in a later sketch using convert entities to grab that sketch geometry. The initial geometry is created with a surface extrude. Remember that a trim is usually always a through-all cut, so a workaround, once we verify incorrect results, is to use the split line and delete face to precisely target the faces that we would like to trim and keep. So sometimes starting with solids is actually a better way to get to a surface body. Solids are always going to give us more faces than a surface body. Usually surfaces we have to create the faces of a model one by one. Using an extrude and a cut, I actually get 6 faces at once instead of doing it one by one with the surface features. So I created some bosses from the front plane, and then, on the right plane, and then I cut them from the front plane to roughly shape the legs. I'm now going to use the surface offset tool to offset the surfaces inward to form new surfaces from the solid body. You may ask, well, why didn't you just start with the outside faces and just delete the faces you didn't need? Why did you have to do an offset? The reason being is that I found an old technical drawing in one of my Eames coffee table books, and it had a 2-inch inside radius. So I couldn't actually sketch the inside from the other photograph I found, but by offsetting it inwards, I was able to get that 2-inch radius and add it with the fillet tool to the offset surfaces. So I add the fillets, and now these solid bodies are no longer required, the transparent bodies you see on the screen. So I'm using the body delete tool to remove them from the model, and now I have both the spine and the legs of the chair completed, but those were the simplest features. The seat back and the seat pan are going to be a little bit more complicated. To create these, we're going to rely on the surface features in SolidWorks. In order to generate the surface features, we're going to have to use 2D sketches and project curves, and potentially 3D sketches to use to define section profiles of the seat back and a seat pan. Once we have our curves created, it's just a matter of dropping the surfaces in between the curves that we have created. I'm going to model for manufacture. In the mass production of this chair, the seat components are molded oversize, and originally they would have been hand routed via jig, and nowadays CNC technology is used to cut the shape. Following the same process in SolidWorks has its benefits. The boundary surface is typically best created between a framework of 2 to 3 to 4 curves with junctions that are roughly 90 degrees to each other. When we start rounding the corners, it's impossible to determine where the profiles in one direction start and end. I would have to use the surface fill tool to model the surface like this versus using the boundary surface of the surface loft tool to model the surfaces as roughly square and then trimming back to their final rounded form. So I'm going to start laying out the seat back. I know that the seat pan is 3/8 thick, and I wasn't able to actually sketch the outside middle profile, one that would come directly in contact with the back, but I was able to sketch the back of the panel, and so by adding a sketch offset, I was able to position that curve appropriately. Whenever possible, I try and use arcs in these layout sketches. They can be easier than splines to control. I also like sketching a chord between the arc and then dimensioning the height of the arc from the chord instead of the radius to match the photograph that we have. I'll add a couple dimensions and lock things down. Note that this arc is actually, it is an arc. It looks straight, but I just have a very, very high radius on this arc. This allows me a little bit more flexibility going forward. I can always decrease the radius of the arc and curve it and make it give it a little more round to it, but it looks straight enough as is. It just gives me that little flexibility going forward. So let's take a look at the layout of the seat back. The front layout is created to a plane normal to the side layout, and jumping into SolidWorks, this will be a little more easier to see. So I've gone in and I've right-clicked the top of the part here, and I've gone Tree Display, Show Flat Tree View. I really like this feature. You can go in and none of your sketches or features are absorbed, so that way it's really easy to jump through and see all of the sketches that create a feature. So here is that sketch on the right plane that we previously saw in PowerPoint. This sketch will represent the profiles. This profile will be the middle of the chair, and then this profile actually represents the very outside edge of the seat back. Now it's currently on the right plane, but here's that normal plane. So if we rotate the view, you can roughly see where the plane is sitting in relation to the photograph. And finally, I have a sketch on that plane that roughly defines the shape of the chair back. Note that we're going to later trim this. This is just to generate our rectangular profile. Well, more trapezoidal than rectangular. I have an arc at the top and the bottom of the sketch, 2 straight lines connecting them. I've next created planes at the top and the bottom. These just pass through these 2 points. Likewise, the top plane passes through these 2 points. And now I can start creating sketches that will define here's the side, and then I'm projecting these with a project curve feature. And here I've created a 3D curve by projecting this curve onto this curve, generating this 3D profile here. A good way of thinking about that is if we were to create a surface extrude of each of those sketches, the resultant intersection would be a 3D curve in space, and this is our project curve feature. I've created a matching curve on the opposite side, and now I'll start sketching the top profiles. Let's take a look at this sketch here. So this sketch is used to define the top of the seat back, and I've used a style spline, and I've made it coincident to the top of the projected curve. So you can see that I'm starting to create a network of curves together, and by projecting them, the 2D sketches together, I'll get a 3D curve that perfectly lines up here that follows this profile along with following the arced profile that I set up in the front layout sketch. I love the new style spline here just because it creates a little bit smoother geometry, and then I've mirrored the spline in the same sketch to have a symmetric profile. I've done a similar feature on the bottom, but here you can see once we hide the planes, let's just turn them all off for a second, that the network of curves we're generating is started from the 2D sketches, and finally we get these 3D curves. Once our curve network is set up, it's very, very easy to use the boundary surface tool. And here the boundary surface works on direction 1 and direction 2. I prefer boundary surface over the loft just because boundary offers a little bit greater control in the second direction than loft does. So in the first direction, I have the top curve and the bottom curve. If we turn off the mesh preview and the curvature combs, it'll be a little more obvious to see. So I'm creating a boundary between this profile and the bottom profile. And then in the second direction, my boundary surface passes through that outside curve we set up, through the curve that represents the middle of the chair, and that I was able to get from the photograph and then offset it to its correct location. And finally, the last profile on the right side of the seat pan. So now I've been able to quickly create that boundary surface from the network of curves. So I'm using project curve features because I love the functionality. I get a sketch in 2D, which is really intuitive. Everyone knows how to create sketches on planar faces. 2D sketches are really easy to work with. Instead of trying to manipulate a complicated 3D sketch to get the exact shape you want, sketch in 2D and then leverage the power of project curve to build the curves that you need. The boundary surface, once the curves are set up, it's really easy. People are intimidated by surface modeling, but if you think of it in terms of the edges that the surface needs to be, you generate curves from 2D profiles. It's just a matter of dropping in the surface over the curves that you've created. So here, if we trace everything out, we see profile 1, the first curve, the second curve, and in direction 2, we see the 3 curves that the surface passes through. Well, now we have the square shape, well, trapezoidal shape of the seat pan. And let's take a look at trimming this out. So the first sketch I create is on that layout plane, that plane that's roughly normal to the seat back. And I've just thrown some sketch fillets in to represent these rounds. I'm not actually going to trim with this sketch. What this sketch does is allow me to use a sketch fillet to quickly dimension the overall size of this radius. And then in a second sketch, I've added a spline with the equal curvature option, and I've manipulated the curvature handles to have a really nice, smooth transition. If you saw our surfaces and splines, my Monday presentation, you'll realize the importance of the quality of curvature in your transitions. If you missed that presentation, but you're still interested in learning a little bit more about splines and surface modeling, the session is available on YouTube as well as available on the Damani Group website. If you're on YouTube, just search surfaces and splines. If you're on the Damani Group website, we list all of our previous SolidWorks World presentations on our tutorials page. Now you may ask, well, why didn't I just create the splines in the same sketch that I had the sketch fillets in? Well, in my experience, the sketch tends to overdefine itself. By converting the sketch fillet into a new sketch, I've eliminated the solver trying to solve that in this sketch. Now all it has to do is just solve these splines because the rest of the geometry is converted in. With our layouts or with our trim sketch set up, all I need to do is create a surface trim to shape the seat back. So here we see the seat back shape. We're using these curvature continuous splines, and a second sketch using a first sketch to prevent the solver from over-defining our sketches. So the seat pan setup is a little bit simpler. The seat pan features these these planes. We've got a sketch here. This was converted from our original layout, and all I had to do was create one more sketch in the middle. And this sketch I was kind of guessing at. I didn't really know what it looked like. So I built it and then tweaked it a little bit and looked at the LCM chair I had in front of me until I got it right. Sometimes we may need to mirror a projected curve. I am using a projected curve here to generate kind of the top edge, kind of maybe the tangent point to the top plane of the front arc as the seat pan kind of waterfalls over. And so I'm creating a 3D sketch from the project curve. It's easy for me to convert the project curve into a 3D sketch. From there, I can create a surface extrude from the top plane, and then I can mirror that body and then convert the edge into a 3D sketch. So you can't actually mirror a projected curve, but this workaround allows you to get the same result. So the seat pan boundary surface, really easy. Once I have this profile, the middle profile, and the right profile, in the first direction, I have the back profile, and then I have this edge that I kind of guessed at. Bam. Drop my curves into the appropriate boxes in the boundary surface, and the surface is generated. I also need to trim the seat pan to shape. Here, the trims weren't necessarily fillet-based, so I just used some dimensions to approximate where I thought that the transitions started and stopped. If we zoom in really carefully at this edge here, you can see there's a slight mismatch between the black line, which is a sketch, and the faint red line, which is a surface edge. This is going to create a little tiny edge in our model because we don't quite have enough material to trim. Workaround: surface untrim or surface extend can be used to add a little bit of additional material to the model. So here I've added 5%. I don't really know how the percents correlate to how much the surface is being extended. Surface extend allows you to plug in rational dimensions. Once I added some material, it's very easy for me to trim the shape, and now I have the 5 completed surface bodies that make up the master part. So let's now move into detailing the child parts and creating the molded plywood pieces. First, I need to propagate the model into the child parts. I'm a huge proponent of using insert part. Insert part, in my opinion, is the best way of pushing geometry from one part into another. The reason being is that under the insert part dialog box, I can bring in solid bodies, surface bodies, axes, planes, cosmetic threads, unabsorbed sketches. It gives me a lot more power of bringing geometry in the child parts versus, say, maybe right-clicking from the solid bodies folder and insert into new part. This is my preferred method of getting master models into child parts. Once we're in the master model, I'll use body delete. Just because this is SolidWorks 2014, I have to delete all the unwanted bodies. In 2015, they added a great feature called body delete, or maybe body keep/delete, something along those lines. It allows me to pick a body to keep or a body to delete. So in 2015, I could have just picked the seat pan and it would have deleted everything else if I had selected the keep option. So now, all you guys are wondering, why did I work in surface bodies instead of perhaps solid bodies straight away? And I have determined that there's three benefits to using this technique for creating molded plywood, and it may also work if you're doing stack-ups of laminates. I don't personally work with those, so you'd have to judge for yourself. The first, thickening a surface body, it creates an edge that is normal to the surface. So this mimics the action of a trim router going around and trimming that panel out. You can see here that the edge is normal to the surface, whereas on the flat face, the edge is also normal to the surface. I have the option of creating a distinct body for every ply. I'm thickening the first surface body, and then offsetting the bottom face and thickening that, repeating until I've completed the stack of veneers. And the molded panel is considered an assembly of multiple veneers of wood. By using multiple bodies and converting my part into a weldment, I have the option of tracking each of those bodies, adding unique properties, and having those propagate onto the drawing. So the first thing I do in the part is set up ply thicknesses. I love equations and global variables in SolidWorks because they can automate and control a lot of dimensions for me automatically. And once I change a variable, the whole part will automatically update if set up correctly. I know that the seat pan has a ply thickness of 3/8 of an inch, and there are 7 plies in the stack. I'm assuming that the outer plies are going to be thinner because typically they're of higher quality of the inner plies, and by cutting them thinner, you get more yield out of a log. So then to calculate the outer plies, I simply take the ply thickness, divide it by the number of plies minus 1, divide by 2. This gives me a 1/32 ply thickness, and then the inner plies is 1/16 of an inch. By changing the overall thickness or / the number of plies, I can instantly update and have my model adjust accordingly. So into SolidWorks here. So here we see the insert part feature. I'm bringing in the surface body. I'm deleting all of the other bodies, leaving me with just the first surface. We know it's a surface because it doesn't look like it has any thickness. We see the surface body, and we also see a blue or a red outline. I have changed these surface outlines to red in my SolidWorks. Next, I'm using the thicken command to add thickness. Note that I can't actually set the thicken to be equal in the variable box, so what I have to do is double-click the feature after creation, find the dimension, and now I can link it to the global variable. The next step is to offset the bottom face and thicken. Note that I do not have the merge result on. What this is allowing me to do is generate those individual solid bodies. So rolling through the tree, I continue to offset and thicken the panels until the completed plywood form is created. Note the weldment feature in the top of the tree. This is added by going Insert, Weldments, Weldment. I can't actually select it because the part's already a weldment. And what this does is change my solid bodies folder to a cut list. And the cut list gives me access to some additional options. So if I were to right-click a folder in the cut list, I can go to Properties. No, it's taking us. Here we go. And then I've added the veneer and the thickness call out to each of the bodies in the cut list. I unfortunately can't use the material option because this continues to always override looking for a weldment material which is not specified. I think that comes from the weldment part if you're actually using weldment for generating steel welded structures. I can also go to the property summary and see, in this case, thickness. I can link thickness to the global variable, and veneer, I can go through. I had to manually type these things in to get the evaluated value. So we're creating the first ply by using thicken, continuing to offset surfaces in the stack and adding thicken to create the veneers. Finally creating weldment, because this gives me options to add additional properties to the bodies. And then I can finally publish the cut list to a drawing. This is a very simplified drawing. All I wanted to show you was that the thickness, or the cut list does come in. We can see the thickness. We can see the veneer. We could also perhaps add an orientation column to control what angle the piece of veneer is oriented in the stack up. And finally, we can do a little call-out drawing here showing which veneer is which in the stack. So, moving on to our next example. Getting the most of the best to the greatest number of people for the least. Charles Eames. After conquering molded plywood furniture, the Eames moved on to trying to create an even simpler and more cost-effective chair. And that was the Eames Fiberglass shell chair. And here is the chair in SolidWorks. The beauty of these chairs was they featured a whole ton of different bases. So this was called the Eiffel base. This is the aluminum group base. They all are interchangeable and universal. The Eameses strove to design modern, functional, and reasonably priced furniture. And the fiberglass shell chair might have been the ultimate realization of this vision. First manufactured in 1950, it was the first one-piece plastic chair not covered in upholstery. It used chopped glass fibers, and Charles really liked the authenticity of being able to see the material. He didn't want to cover it up with upholstery. He liked the beauty and the authenticity of showing the production material. The chairs were made by impregnating a glass fiber mat with resin and then forming in a core cavity steel mold mounted in a hydraulic press to cure the resin. So we're going to be reverse engineering this shape today, and the fiberglass chair appears as one large sculptural shape. During the design process in the late 40s, the Eames office employees would hand sculpt plaster molds to produce prototypes. And the organic nature that this chair embodies is free from the influence of CAD. Modern CAD's great. I love it. I use it every day. But something must be said for the purity of form developed by human hands. When you're sculpting a shape, you can't add a perfect 1-inch fillet. You're going to have a natural lead in and lead out as you sand the material and work with the form with your hands. And by harnessing the power of solid modeling, we can develop forms that mimic sculpting by the human hand. Unfortunately, this chair has a ton of curves, blends going on, shapes that seamlessly transition to each other. I would have no idea where to start with a series of photographs. And for example, I know that Herman Miller recently reintroduced this chair, and if they didn't have access to the original tooling, maybe they needed to create a modern 3D CAD representation to have tooling for this chair reproduced. In this case, I have had the chair 3D scanned. We do have a 3D scanner at the Damani Group. For more information, we have a presentation up on our website explaining some of the processes and setup that go into 3D scanning. Regardless, the end result of the 3D scan was a STL file that can be opened in SolidWorks. But STLs in SolidWorks, they don't function like other traditional solid geometry. They actually come into SolidWorks as a graphics body. You have the option of bringing in all of the little individual triangles as surface features, but in my experience, you're going to crash SolidWorks if you even get it to open. So you're stuck working with the STL graphics data, and the graphics data cannot be sectioned. So I would love to be able to throw a ton of sections in here. I could simply trace over the sections, create curves, drop my surfaces in, and create the shape of the chair. But without sections, how can I section the STL? Well, there is a workaround. First, I'm creating a comparison assembly with the scan chair in orange and then the final surface chair in gray. If our final surface model has this patchy, molted appearance, that means that we're really, really close to the original scan as, our surface data undulates in and out of the scan data. So, sectioning STL graphics. There is a workaround. We can extrude surfaces into our model and then trace the graphical intersection of the surface plane or surface extrude with the STL graphics body. So let's jump into SolidWorks. Here we see the completed chair with all the various patches that went into creating it. But the first thing we need to do is start defining what we know. So what I've done is extruded or created a planar surface on the right plane, and now it's very easy for me to see the intersection of the right plane with the graphics body. So I've created a 3D sketch, or sorry, this is a 2D. Next one will be 3D. Here I have a style spline, and once the style spline is sketched, I just grab the control points and start moving them around and gently dragging them until my curve perfectly matches up with the scan data. I can't actually work directly on the right plane because I can't see things. So when reverse engineering from scan data, I feel that you have to really kind of work in 3D and rotate the view to exactly see what you're doing and move the points accordingly. But it's really easy to just gently massage the points of a spline and get it to line up. Yes, question? No, I cannot intersect the STL body. So the STL body doesn't actually have any physical or surface data. It's just an on-screen graphical preview of the scan. So if I were to create, let's just grab an intersect curve, it won't even let me pick this. Right? I'll do a box select. No, it's not going to let me do it. The reason being is the STL is just triangles. It's just a point cloud with triangles dropped in between them. So if I zoom in really close, we can start seeing some of the individual triangles. It may be hard to see on this monitor. It could just be a wash of color. So I actually have to go in and I'm going to have to manually trace every single curve on this. There are some software add-ins that will automatically surface scan data for you. I'm just not 100% familiar with them. This is my workflow for reverse engineering from scan data. The next thing I'm going to define is, let's hide this. The other downside of working in an assembly is that I can't click a surface body and hide it. I have to expand my surface bodies folder, and then I can hide it directly. So what I'm going to do is start sketching the outer profile. I know what the outer profile is. Sometimes the scan can't pick up the exact details, so I might have to guess when it's a little jagged here. So I'm breaking the shape up into 3 sections, and I'm going to use create sketches on planes that make most sense to me. Here it was really easy for me to create a spline. The dimension is just for me to kind of lock it down. It doesn't really mean anything. And then from the front plane, I was able to trace the shape of the back, and then I can create a curve feature and evaluate if the curve is matching. Sometimes the curve will get hidden by the graphics body. I don't know why, but if you select it in the tree, it will show up, and you can see that it's highlighted and see that it matches. If I rotate the view, there, it disappeared from the graphics window. And it may be difficult to see on the projector. I can see it perfectly up on my screen, but I'll leave that judgment to you. I'll continue to create projected curves to define the outline of this shape. So here I have a sketch on the right plane, tracing this bottom edge, and then I have a sketch on the top plane. Finally, I'll do something similar, creating this front edge. Now, some of you may ask, well, why don't you just create a single 3D sketch and trace that? I would hate having to sketch all the different points, control all of the different spline handles, and get the 3D sketch to perfectly match this in space. I found it way easier to simply create that sketch on the front plane that matched this curve, create a sketch on the top plane that matched the curve, project the two together. I'm working in manageable 2D sketches, creating 3D curves with Project Curve. It's my opinion that Project Curve is one of the most powerful tools in SolidWorks surface modeling. It allows you to start in 2D, end up in 3D, and create surfaces from the 3D curves. Note that I haven't created the blends joining these sections together. I find that's easier to do in the final 3D sketch. So in this 3D sketch, I've converted each of the projected curves together and joined them with a spline with the equal curvature relation, and then I'm adjusting the handles to match the shape. The scan might be slightly off on the edges. The scanner can have some difficulty resolving sharp edges, but it's close enough for me. I think it looks spot on to our scan. So this is what I know. Everything else I'm going to have to start guessing on. But I'm going to be taking very, very close, educated guesses. If we jump on to our next part, don't want to save anything. So we're defining the perimeter. A little bit of background for those of you who may not be familiar with surface continuity. Surface continuity is the quality that we're connecting surfaces and curves together with. If they come to a sharp point, we have what's called C0. We can evaluate this with the curvature comb or the curvature display. This is called zebra stripes, and we see this pattern on our part. If the stripes don't touch, it means we have a sharp connection. In a tangent connection, the stripes touch, but they touch with a sharp edge. This indicates that we have a tangent connection, but the radiuses are not the same. Here we see one arc with a certain radius, a second arc with a constant radius, and a third arc with a constant radius. This is what the standard fillet tool gives us. With splines or using surface features with the curvature option, we actually see that the radius on this blend is changing. The radius starts equal to this arc, increases along its length, and then decreases again to match this arc. We can evaluate this with the zebra stripes by seeing a smooth connection of the stripe. There is no break or hard break here, as we see with the C1 tangent condition. We can also evaluate with the curvature display. Here we see on the C1 we have a constant radius indicated by solid color. The radius is changing in this connection because we see that the gradient here is showing the radius is changing along the length of the curve. So before we start creating surfaces used to section the model to generate sketch geometry on, I'm going to break the form of the chair into 3 types of surfaces. This is just my terminology for it. Other people may call it different things. I just find it kind of helpful for explanation purposes. The first type of surfaces are primary surfaces. They're large and relatively flat. The seat pan is a primary surface. The side here is a primary surface. The back is consisting of 2 primary surfaces, and the armrest is the same. Note this line down the middle of the chair. I'm going to do half the work by modeling half of the chair and then mirroring over the right plane when completed to form the opposite side of the chair. The next type of surface is a blend surface, and these connect primary surfaces together. They can almost be thought of as fillets. They're not actually using the fillet tool. We'll be manually defining these with the boundary surface or surface fill. And finally, the last type of surface are transition surfaces. These complete the areas of the chair that transition from one area to another. Here we see the transition surfaces along the front of the chair, transitioning from the seat pan to the front edge. We see the transition surfaces transitioning from the seat back to the rear edge of the chair. And finally, we have some other transition surfaces transitioning from the armrest into the back here, as well as this surface transitioning from the armrest into the transition here of the chair. Primary surfaces. They primarily consist of 4-sided boundary surfaces. They're constructed from 2D sketches, 3D sketches, and projected curves. They're the first surfaces that get built in a surface model. We can use section surfaces to help trace sketches over the scan data, and then we can create blend surfaces. Blend surfaces consist of 4-sided boundary surfaces and occasionally surface fills. They're mostly constructed from existing model edges using 2D and 3D sketches to define the shape of the blend. For example, this blend surface is a blend between this edge, and I have a sketch here and a sketch here to shape this blend. Sometimes I don't require surfaces or guides between them. For example, this large surface here is simply created between this edge and this edge. You can kind of think of them as fillets. The standard fillet tool gets applied to existing geometry. Likewise, blend surfaces get applied between existing model edges. Finally, we have transition surfaces, and these are 4-sided boundary surfaces or 3, 5, or more sided surface fills. They're constructed by 2D sketches and projected curves to get form, and they usually use existing model edges as well. The transition surfaces connect the different regions of the chair together. They're the last step because they can be the trickiest. We don't necessarily know what the shape of the surface wants to be until we have the surrounding surfaces created. So I'm starting with a sketch on the top plane, and I'll use that to create a surface extrude. I'm kind of guessing here in this view where the blend starts and stops, where my primary surface connects to the blend surfaces. So that's why I have these dimensions here. With the dimensions, I can go in and easily tweak values after the surface is created to try and match the scan data precisely. So here I have my surface extruded into the model. And if we look from the top plane, we'll see that these are all actually arcs. I can't create a 2D sketch on an arced face. I need a planar surface or sketch plane to create the geometry. So I've gone in and I have a plane here that's connected between these 2 points. And this allows me to create a sketch, and I'm working in the 3D sketch environment, in the assembly, and I'm adding my spline and tweaking the control points so that way it matches the scan precisely. With our section planes, it's really easy to see where our surfaces intersect with the STL body and generate curves accordingly. When I'm done with the surface planes, the layout, I can use body delete to remove them from the model to keep a nice clean tree. If we hide this guy, because I'm modeling half of the chair, I need to control the shape of the surface along the mirror plane. And to do that, I'm using a surface extrude feature. So I just have a flat surface here. If we show that surface, this is extruded from a edge or a sketch that's been converted from my right profile that I previously created. And now I'm creating that boundary surface between that model edge and the 3 projected curves. I've used tangency to face here to ensure that I have a smooth tangent connection on the mirror plane. I want my surfaces to mirror like this. I don't want them to mirror like this or like this. I don't want a hump or a spike where they hit. I want them to be perfectly flat. One thing to be aware of is that you may need to increase the tangent influence on that reference surface. Here we see that the curvature is changing as it gets close to the reference surface. By increasing that to 100, I've now smoothed out those changes and gotten the correct surface that I need. I see that molded appearance. I know I'm very, very close to the scan. And I can continue to develop additional section surfaces to generate geometry. Here I have surfaces extruded through, and I can clearly see where my curve needs to be created. I'm using the curve features to generate them, cleaning up. I like putting all this layout stuff in a folder so I have a really nice clean tree at the end. All of my setup and section is in a folder, and now I can create an additional boundary surface between these points. So we're using the projected curves to get our geometry, building geometry with a boundary surface, using surface extrudes to guide symmetry as required. And sometimes we may want to break a boundary surface up into smaller multiple boundary surfaces. I actually created the back of the chair with 2 different boundary surfaces. I created one for this relatively square-shaped surface, and then another for this surface that has an arcing top face. I'm a huge advocate of breaking surfaces down into as many square patches as possible, and then connecting them with the curvature to face option. Once again, you may need to increase that tangent influence. Use the curvature combs of the surface to evaluate the quality of the connection. And here's my rationale between doing that. By splitting the surface up, the UV curves, which are the underlying math of the surface, can better be controlled. In green here, I have the entire surface created as one boundary feature. Then Yeah. Sure. So in my opinion, it's better to break surfaces up. So the reason I'm breaking things up is I want to control the UV curves, which is this slide here. So the green is created as one surface. And UV curves can be created, I think it's going to face curves. And so what this is showing is the actual kind of math is following a path that looks like this. The U in one direction, the V in another. Here we see that I actually have a profile here on the bottom, a profile here in the middle, and a profile here on the top. And so the UV curves are shaped by the overall shape of the surface. By breaking it up into smaller patches, I can better control the UV curves, and in my opinion, the UV curves end up looking more like what the shape wants to be. I found by breaking things into smaller sections, I can eliminate ripples and tweaks. I wanted to have as few as profiles in a surface as possible. Here, I simply have the 4 outside profiles. Likewise, on this surface, I have the 4 outside profiles of the surface. Here, I have to have an inside profile to define the shape. So I'm breaking it up and connecting multiple smaller surfaces together with the curvature to face option instead of trying to do too much with one surface. So the majority of our primary surfaces connected or created. Now it's time to connect them together using blend surfaces. And blend surface isn't a special feature in SolidWorks, it's just what I'm calling them. I'm mainly building them with the boundary surface. So I'm connecting the primary surfaces together with the boundary surface tool. Here I don't have any guides shaping this surface. I just have this edge and this edge. And there's a feature in boundary. There are these arrows that control what I believe is called the tangency length. And you can grab these arrows and change the length. And this will affect the curvature comb. It's almost like dragging the spline handle if I had created a 2D sketch connecting this edge and this edge. So let's take a look at the blend surfaces. That is the wrong file. Bear with me a second. Ignore this pink line here. Sometimes boundary surface glitches out and shows you a random pink line through your surface. I don't know why it happens. The only way I know of fixing it is closing SolidWorks and reopening it, and that's just a little bit too much for our presentation today. So here is we'll edit the part in the assembly. We can see that we have that molted appearance of our final surface. We're very close to the scan. So I've connected this edge to this edge with the curvature to face, and I'm using the handles to tweak the shape of the surface. And if you uncheck the apply to all, you can actually drag the handles on opposite sides of the boundary surface. With apply to all checked, they move equally. Likewise, I can grab these and adjust the shape of the surface to very closely match the scan, as well as having a really nice curvature comb where we have a nice gentle ramp in and a gentle ramp out. We don't see any glaring spikes or degradations in the curvature of the surface. So continuing on, we may need to start adding some trim features at this point. As I said before, the boundary surface and the blend surface should always have 4 sides. If I had created a boundary surface to this point, it introduces what's called a degeneracy as the UV curves bunch up to 0 at this point. Try and avoid it at all situations. It can have really, really bad effects on offsets, on thickens, and on shell features. I'm adding some construction geometry to locate where this spline is on the surface, and then I'll use that to trim out the shape. I can also create blend profiles to give me exact control of what the blend looks like. Here I have a planar face or a planar surface, and I've used that to section the STL body and get a visual intersection. I also used that to create an intersection curve here, and then I converted this edge into the sketch. In my opinion, it's always best to connect splines, especially with the tangent or the equal curvature, to existing sketch geometry. So convert model edges or convert surfaces into your sketch by using intersect or convert, and then adding the relations to that sketch geometry and not to the model edges. So there is the trim for our corner blend, and you can kind of see where I'm going to start connecting surfaces. I'm going to connect here and here. So I have a folder setting up my blend profiles. And then let's take a look at the sketches that were used to create the blend. So here I converted this edge of this existing surface. Sometimes it can be easier to jump into the part. So if I were to exit the sketch at this point, then I don't have I'm not looking at both bodies at the same time. So what I will usually do is set up the sketch at this level, then jump back into the assembly and perfectly tweak this spline to get the shape I want. So I can manipulate this with the handles to A, get really nice curvature using our curvature display, and B, match the scan data. So with that profile set up, I can create an additional profile here, and now it's just a matter of connecting the two primary surfaces edges together, and then connecting or adding these two profiles, which connect our blend. I have to increase the tangent influence to 100% here. If I was to decrease these to 0, we actually see a big spike in the curvature. So I actually have an inflection in my surface. By increasing that to 100, we eliminate that inflection and get nice smooth curvature along our surface edge. So to tame those those spikes, increase tangent influence to 100%. We can also use 3D sketches to connect blend areas together and use those as profiles. Let's take a look at using the 3D sketch in our next blend. There's a little known feature with splines and with actually any sketch geometry, and it works in both 2D and 3D sketches, and it's one of my favorite relations in SolidWorks, and it's rare. I find that a lot of users don't know about it, but it's such a powerful relation. So I'm going to draw my 2-point spline, and I'll add equal curvature. This is a pretty standard relation. But I'm going to next add a curvature to face relation. If I pick the spline, I pick the model edge, and I pick the face, I get tangent face and equal curvature face. So what this does is actually add an equal curvature relation directly to this surface. I can't use an intersection curve in a 3D sketch. Where would I create the intersection plane? What would the intersection be? So I can use that equal curvature to face option that parametrically moves as well as I move this up and down the surface body, and then I can tweak the handle as required to get really nice, clean geometry. So really, really cool relation. Once again, that's grab the spline, the model edge, and the surface body, and you can get the tangent face or the equal curvature relation. Works both 2D, 3D sketch, lines, arcs, splines, any sketch geometry. And finally, we're going to complete the corner blends. We've previously trimmed out this area here, and now it's just creating something that kind of looks like a fillet going around the corner of the part, but it is surface geometry. And sometimes the boundary surface, even when increasing the tangent influence to 100%, we get these nasty spikes here, and I can't get this ripple out. Hopefully it shows up on the projectors. The workaround here is I use surface fill. What surface fill does, it's going to generate an oversized four-sided patch and then trim it back to fit. So if you're getting poor results with boundary, try a surface fill. It may clean up that geometry and give you the exact shape that you need. So when our blends are created, we need a way of evaluating the quality of our blend. And I'm evaluating these connections with zebra stripes. So zebra stripes can be imagined as putting the part in a dark room with a series of fluorescent overhead lights and shining light on that part and just seeing how the light flows over the part. A really good curvature continuous connection means that it's very difficult for me to actually see where one surface starts and one surface connects to it. So here we see our zebra stripe seamlessly passing over the surface. Likewise, coming down here, we see our zebra stripe seamlessly living between two different surfaces. If I had turned off the surface edges, you wouldn't know where one surface started and the other surface stopped. You can also use the curvature display to evaluate curvature continuous connections. Here we want to see a nice gradual transition between. Sometimes you will get these little triangle pockets. I think they're just graphical glitches. In my opinion, zebra stripes gives you a little better idea of how the surface looks as we evaluate the highlights of the surface and the connection between them. With the majority of our blend surfaces complete, let's start on our blend transition surfaces. We'll continue to define the shape by creating section surfaces and using style splines and projected curves to generate our geometry. So if we jump back into our assembly here, move on to the next example. Take a look at two of the transitions that are present in this chair. Need to edit the part. Here I've created another set of surface extrudes. I can exactly see where my profile is by creating a sketch on these faces. If it's a non-planar face, I generate that curve. And then finally, I can create the surface. I'm using the style spline here. I love the style spline and how smooth it is and how nicely we can connect it to other geometry. So here I have an intersection curve sketched. And then I've made the style spline equal curvature to my reference. And style spline has a certain number of points, and it's dictated by the curve degree. The higher the curve degree, the more points you have to sketch with. Note that when you add the equal curvature relation to a style spline, you take up the first two lines or first 2 points. They are locked in. Likewise, if you add a tangent, you lock up the first line and first vertex in a style spline. If you need more points, you can increase the curve degree to give you more points and more control. Here, if we see the lower we decrease, I can't actually move these points. I'm very limited in what I can get. So by adding points to a style spline, we have additional control and use the style spline to match exactly what our scan indicates. With that created, I can create a boundary surface. One thing to note, I have that big outer profile 3D sketch that I created at the very top of the tree, and I'm not going to directly reference that. I created a second 3D sketch. Here you can see it here, and I can just converted the relevant entities into that 3D sketch. This is to prevent that big outer layout 3D sketch at the top of the tree from being absorbed into subsequent features. Also, I'm not hunting for it. Say it got absorbed into a feature really high up the tree, I have to find that feature, expand it, just to find it to use it in other geometry later on in the tree. The next transition we'll look at is this really tricky transition here. So we're going to build this surface and then the transition between them. So just to recap, style splines, awesome to a level of control, really, really smooth curvature. They have smoother curvature than the traditional spline tool, and we can use the curve degree to tweak how many points we have and how much control we have over the surface. Sometimes when we're modeling, we have big spikes in the curvature here. Let's take a look at that actual surface. Jump back into our part. It's going to work at the part level, so it's a little easier to see the curvature combs, and we don't need to work with the scan. Roll down the tree a little bit. You can see that I'm putting all of my setup stuff into folders, and note no lack of solid geometry. Tons and tons of orange features that hopefully we'll get back in SolidWorks 2016 when they add our colors back. So this is I played around with this surface forever. I played around with different profiles, maybe having a plane here to sketch this on, and I could not dial this giant curvature spike out. See what's happening in the curvature? I could not get rid of it. And so sometimes it's easier to just get 95% of what SolidWorks gives you. Take the good, cut away the bad. So I could not get that spike out of there, so all I did was just trim it away, and then I'm left with really nice clean curvature that I can use to create the transition between the armrest and the seat back. And I'm using surface fill. I could have maybe used a series of boundary surfaces, maybe boundary from here down to here, maybe a boundary surface here to here, but I didn't really know what that looked like, and it was hard to set up sections, surfaces, and accurate projected curves from the sketch. So I'm going to harness the power of surface fill. Surface fill, in my opinion, is really, really powerful, but it has to be used properly. What surface fill does is we can see this yellow four-sided grid. It's building an oversized four-sided surface, and then it trims it back to fit within the profile. Surface fill takes its shape from surrounding geometry. So if our surrounding geometry is set up really well, there's a really good chance that surface fill is going to perfectly match our scan. I also don't default to curvature on all edges out of the box. I start with tangent on all edges and then add curvature as required to perfectly dial in the form. Note that the last edge of this is unconstrained, so I actually have a 3D sketch here that was constructed from a projected curve, acting as contact, guiding the final edge of this surface fill. So let's take a look at the fill versus our scan and just see how it looks. So the downside of surface fill is that I don't really have any control over the inside of it, but if we look at it, we're really close. We see the undulation, we're seeing both the scan and our surface data, and we've got a really, really good result here. So to clean up those curvature spikes, I trim away and then default to surface fill for creating tricky transitions between forms. On the front of the chair, I'm going to guide another surface fill with a boundary surface. This allows me to control the shape of the surface fill with the boundary surface and then complete that three-sided transition with surface fill. I'm going to convert to solid with thicken. So what thicken does is offset all the faces and then loft between them to create the last edge. A tip is to mirror first and then thicken. Thicken rarely gives you a planar face along the mirror plane. So by mirroring, then thickening, and then cutting in half, you get a perfectly planar mirror face. But there are some downsides to using thicken and shell. Well, they're not downsides. They're just things we need to be cognizant of and check after the feature has been created. Moving on to our last example in the chair. We can just work directly in this part because we've finished all of our surfaces. We verified that they match the scan data. So I'm mirroring and then thickening and then cutting in half. And my rule of thumb, every time I create a thicken feature or a shell feature in the model, I'm going to turn on check. Bear with me for a second. My laptop's deciding that it's not going to be the quickest today. It's a little bit old in tooth, and maybe some new technology isn't ordered. Thicken features can also take a while. They're really, really processor intensive. It's got to go through and offset every single face in this model and then throw a loft in between them. But there's our thicken and our cut. And now I'm going to run the check tool. This is also under Tools Check. And I'll turn on Stringent Solid Surface Check. I don't really know what it does. I believe it forces a new check every time. And I asked the developers on Sunday doing alpha testing what it meant, and they couldn't even give me an answer. So they don't even know what it means. But stringent sounds good, so let's turn it on. We'll run check, and check is going to go through and check all of the geometry in our model. And it didn't actually give me an error, which is odd, because every other time I've done this presentation, it gives me a geometry error. It's reporting that this face is bad. And if you have geometry errors or general faults in your model, it's a nightmare for adding additional features. If you don't run the check and you don't realize you have a geometry issue, you can add a ton of features to a model. To a certain point, it just stops. It gives up. You can no longer add any features to the model. And that's because there's an issue with the underlying geometry, and the kernel can't merge and knit the surfaces into our model and create the geometry. So the correction for the general fault, it's pretty simple. I use delete face, and I blow away this bad face. This face is going to need to be corrected anyways, because it doesn't actually look like the chair. By delete face, I'll delete the faulty geometry. Normally the check should have reported a face in here as bad, and it will show you a yellow grid preview and point an arrow to the bad face. So I use delete face to delete it, a sketch spline between this edge and a 3D sketch. Then it's just a matter of lofting here, and then knitting in, and then surface fill to clean up the geometry. To complete the chair, I mirror the body, add a fillet, and finally I'll run undercut detection and draft analysis to verify that we have a manufacturable part. That we have correct draft angles for the core cavity, as well as no undercuts. Maybe a small surface decided to bend over itself. The undercut analysis verifies that we have a clean model ready for tooling design. If you're interested in modeling the base of this chair, we don't have time to go over it today. However, I did cover it in my SolidWorks World 2014 presentation, Will It Blend? If you take a look on YouTube or on the Damani Group website, the entire 90-minute session is looking at the fillet tool and techniques for blending various fillets and shapes together. So if you are interested in another form of surface modeling, please check that out. Couple points I want to cover on the base of the chair. It's called a spider. It's a die-cast aluminum part that connects the fiberglass shell to the aluminum base. And the draft tool can provide wildly different results depending on what options we select. We'll get that open. We'll also consider what the core pins in our part do. So there's a couple different types of sketches. Let me hide this. That'll be our next example. So I need to add draft to these ribs for correct manufacturing so the part can be ejected from the tool. And neutral plane draft works by selecting a plane, in this case the top plane, and then it's adding all the draft from this plane. That's the reference. And what neutral plane can do is make things really fat or skinny. So here we have our rib, and the rib got really, really fat. It also expands towards the root here. Neutral plane is not the best option. Parting line allows me to specify an actual edge for the draft to be added. And here I'm adding the parting line from the bottom. And what this is doing is actually tapering the top of the rib so visually they look wrong. We also have a crazy result going on here. That is no longer a cylinder whatsoever. My best advice from using the parting line draft is draft from the tops of features and especially draft from the visual edges of a part. So I'm drafting from this edge because I'm actually going to see this rib on the part. And remember that Charles said the details aren't the details, they make the design. We're really focusing on the details and visually having the part look correct. I'm ultimately going to fillet this edge, so if it gets a little wide here, that's fine. But if we look normal to this face, we have a nice straight looking face because we drafted from the correct edge. So just be aware of where you're creating your draft features from. And that's also important when dealing with round holes in models. So let's jump. I'm going to create a cut on this face here. Here are our holes, and then I'll use the parting line draft tool to quickly add draft to the hole. Now what I did here was grab an offset of these surfaces and extend them to show you what this produced. I created a sketch on the top plane with an intersected. So this is actually a spline, this is a spline. These are not round holes. Holes in most molded parts, not all holes, but a lot of holes in molded or cast parts are created with core pins, which are off-the-shelf components. I want the core pin to be perfectly cylindrical passing through this clearance hole. It's just a loose clearance hole for a bolt that will connect to the fiberglass chair. So if we roll up and take a look at the correct way of creating the holes in this part, so that way our tool maker can use those off-the-shelf core pins. Instead of creating the sketch directly on this face, I need to remember that the part or the tool is separating along the top plane, so everything needs to be cylindrical in regards to the top plane. What I did was I showed my layout sketch that created this form as well as the hole locations. Now I created a plane parallel to the top plane through this point here, and then created the core pin hole on that plane with draft 2 degrees. So this is ensure that when the model is complete, I'll do an offset and extend, and then let's intersect with the top plane. I have 2 cylindrical holes. The toolmaker could buy this off-the-shelf core pin and use it in the design of this part. The last little consideration I want to bring to your attention is the order of fillets. SolidWorks filleting is extremely powerful. It can generate awesome results for us, but the fillet order can be important. So let's jump back in our tree and take a look at these fillets as applied. We'll hide our sketches, make it a little clearer, and also we'll hide these core pin surfaces when SolidWorks decides it wants to respond. There we go. So this is the out-of-the-box fillet. What do we see? We see the sharp tapering fillet here. This is exactly what SolidWorks gives us. But if we look at the actual part, that's not what the part looks like. The part has a much subtler transition here. It's more gradual, it's more graceful. So we put back on our lines. The quick workaround is to add a split line and split this feature here and here, and then use delete face to delete the faces from the model. And what delete face has in the background, if we select delete and fill with the tangent fill option, this is actually deleting these 3 faces and replacing them with a surface fill. And if we turn off our model edges, we have a much smoother transition. We don't see the actual sharp fillet edge like we did in the previous example. When designing molded or cast parts, be aware of the draft tool, what type of draft tool, whether it be neutral plane or parting line, that you're adding, and be careful of what edges you're drafting. Remember that holes in parts are created by core pins. Add features accordingly, so that way the tool maker is happy with you and he can buy off-the-shelf components. And the details are not the details, they make the design. Consider manually tweaking fillet intersections to get exactly what the part needs to be and not what the features in SolidWorks give you. Finally, I'd like to end with the Eames lounge chair. And Charles once described it as the warm, receptive look of a well-used first baseman's mitt. It's a very iconic piece of furniture designed in 1956. And here is the same chair modeled in SolidWorks. Another thing to be aware of on parting line draft. The back of the chair has 2 die-cast connectors that connect the lower panel to the upper panel. And if we were to add parting line draft from this top edge, what it actually gives us is this profile here, because these edges are not parallel with each other. I want the part to be perfectly straight here. I'm really concerned about the details of this back connector. Taking a look at the back connector. So I add the draft tool, or the parting line draft, get my required draft on this part. Oh, wrong plane. We can see that it tapers in and out. It's not straight. So I only want to work on one half of the model, so I'm going to cut in half. And there's my old friend project curve again. So what I did was created a sketch on the front plane here, and then I made it tangent to the very outside edge here. And this generates a new straight edge, just a sketch line. On the right plane, I converted the bottom edge of the part and then projected together. So if we see what the curve is, we actually have a really nice curve that is a visually straight line, even though the draft will be variable along this face. The draft can be easily created by creating a loft or a boundary surface between the top set of edges, that new projected curve, and finally I'll use replace face to get it into the model. I no longer need that surface body, and it can be removed from the model. One thing I also want to point out is always verify the results that SolidWorks gives you. In this case, I wanted to use a full round fillet to add the rounds on the top and the bottom of this connector. So here's the full round fillet tool. Does anyone see anything not right here? Is that symmetric? No, it is not. So I worked around that. It was just something that had to happen. What I did was create a series of split lines. So I created a sketch on the top face and the bottom face, and then I created a boundary surface between them to manually generate that connection that is symmetrical when I mirror the model. So just always verify the results that SolidWorks gives you. Just because it says it's a full round fillet on a symmetric part doesn't actually mean it is. Once again, just verify, verify, verify. Always trust the geometry that you manually create, but be skeptical of the geometry SolidWorks creates until you verify that it is exactly what you want. So the parting line draft workaround to have visually straight edges is to create a projected curve and then loft between the existing model edge and the new projected curve. Once again, consider the details are not the details. Not jumping into SolidWorks, but showing this visually in PowerPoint. Here we have a constant radius fillet. When it's applied to this edge, it actually visually gets smaller. Constant width fillet is actually, or now I think it's now called chord width fillet, is used by dimensioning the chord along this profile, so it visually looks the same size. Remember, the details are not the details. They make the design. The final two examples I'd like to touch on are some techniques for creating natural-looking upholstery. I don't actually work in soft goods, so I can't comment if these techniques are good for generating flat patterns of upholstery. I'm sure people who work in soft goods have their own techniques. I'm more concerned with creating realistic-looking upholstery in SolidWorks, so that way when I create renders, the cushions on this chair really pop. They look really realistic. They don't look like they were created in a CAD software. So real upholstery, it never lays flat. So we want to replace planar surfaces in our model with pillow-type surfaces to give a more realistic look to the cushions. Let's take a look at the armrest. We're going to roll up. This is the completed armrest. So I was able to roughly block this shape out with some solid features. It's just an extrude from this, a couple cuts and fillets, and my shape is complete. I've set up two planes, here and here, and on the planes, let's expand it's not going to give it to me. Okay. We'll hide the boundary and we'll show the sketches. Here the sketches are in magenta. So I wasn't concerned about the curvature. All I did was want to have a quick 2D spline. I grabbed the handles, tweaked them, and now I deleted these inside faces out, turned that solid body into a surface body. And our boundary surface is just created from the outside edges of the armrest with those two spline-shaped surfaces or profiles, and I get my surface. I'm going to complete the transition by knitting the boundary into the model and then using surface fill because I have an awkward transition here. And I don't want the surfaces to look perfect here. The more variability and maybe poor curvature we have, the more realistic my armrest may look. Finally, this face is rather flat looking. I want to pillow it out so it has more realistic upholstered look. And I'm using the boundary surface to do that. I'm not using sweep here because I need to have the path in two directions. So I could maybe do this with the first profile and a guide curve. I prefer using the boundary surface. So the top set of edges is converted into the 3D sketch. And now I have some additional sketches on 2D planes. Here we go. And let's take a look at actually creating this surface. One thing to be aware of is sometimes if we turn off we got to turn off the curvature combs in the mesh preview to make this look a little easier. Hide everything, so we'll pick our 3D sketch. I brightly colored these so they show up easier. And then we'll pick these profiles. We'll pass the boundary surface through them. And actually, if we look at our preview, see what's going on in this area here? Well, it corrected itself a little bit. But I actually, if I were to build the feature now, probably won't build. And it says, the feature could not be created because of self-intersect geometry. SolidWorks doesn't know how to resolve passing this profile along all these curved edges. So if I right-click on an edge and add connector, I can give a little more direction to SolidWorks of how it should treat that boundary surface. So I'm going to add connectors in the unsupported areas. We can see that the preview gets a little cleaner. And eventually, when I click OK, the feature will build. So with that boundary surface, I'm using replace face to get it into the model. And the next step is to create some piping. Piping is really easy to create. I'm simply converting the outside edges of the armrest into a new 3D sketch. I created a circle and then swept it along the path. So here we see the two circles I'm using for the piping. One thing to note is to enable the minimum twist option. Otherwise, I can find that as the circle goes along the profile, it twists. This sweep didn't need it, but the sweep on the top did need the minimum twist option to look correct. The geometry, it was doing some weird things in this area with minimum twist turned off. So by turning minimum twist on, it forces the sweep profile to try and stay as straight and as normal to the path whenever possible. So to recap, creating this natural-looking upholstery, we're creating boundary surfaces to replace, or other surface features to replace flat planar faces, try and puff up the flat faces by adding these pillow-type surfaces, and we can add piping by creating a sweep along the edges of the armrest. The last example of realistic upholstery I'd like to leave you with today is a technique for creating tufted buttons. So modeling tufted buttons instead of relying on a rendering texture or a bump map, in my opinion, produces superior results. So these two faces in this pillow, they are physical geometry. They are not a bump or texture map. I modeled this face. It's actually really easy to do. So we're going to create cushion surfaces in the same way that we created the pillow shape on the armrest. We're going to create a natural-looking boundary surface here. We'll roll back. And now I've created a large trim on the top plane to trim out the area for my tuft. I'm now creating the button. In real life, the button is actually what forms the tuft by pulling the leather down and creating the folds and the creases in it. So just like in real life, we need to have the button in our model. And now I'm creating the real magic of how to create the tufted-looking upholstered face. So I started with a 3D sketch on the top plane, and I dropped a whole ton of sketch points in. So I went skip point, dropped a bunch in. Then I moved to the right plane, and I started moving them up and down, alternating. And I went to the front plane, and I did the same thing. I want to have the craziest looking 3D sketch possible here, with tons of undulations, tons of up and down. This is what's actually going to allow the tufts to be created. It's going, by forcing the boundary surface to fit through that 3D sketch, we force it to take on that really unnatural look. In order to seamlessly fade all those creases out, I added the curvature relation to the closed outer profile. I increased the tangent influence to make it a little bit smoother. And finally, this is a little bit of guess and check. A lot of the time you will get self-intersection as the surface kind of folds over itself. So all of these pink lines you can see here are connectors. The same way I added them to the armrest, I right-clicked, added connector, and then I started a manual process of dragging them around until when I clicked the green button, it built the surface instead of reporting self-intersection. The rest of the pillow was easy to complete by mirroring across. And if we take a look at the actual chair, I did the same thing for the smaller cushions. We get really realistic, natural-looking upholstery, and all it took was one crazy-looking 3D sketch. Probably the only time that you actually want to have a whole bunch of nasty creases and folds in your boundary surfaces. Normally you're aiming for that really clean geometry, but this time we want to create the nastiest geometry possible because it really creates that realistic looking leather appearance. So the magic is that tough sketch. Start from the top plane, drag a bunch of sketch points, go to the right and the front planes, move them up and down so we have that undulating 3D curve, create our boundary surface between them, add connectors as required to prevent self-intersection, and the completed Eames lounge chair. So I thank you very much for joining me here today. If you like this session, please take a couple minutes to give your thoughts via the 2016 SolidWorks app. It keeps presenters like me coming back every year.